What we've been working toward up to this point related to all of our complex number skills is going to be used in Demoivre's theorem. And I think we talked a little bit about Demoivre on Thursday of last week or sometime. Last time we met. Demoivre's theorem gives us a shortcut way of taking high powers of complex numbers and also taking roots of complex numbers. All right, so let's just start off with what the theorem is, and then we'll work a few examples so you can kind of see how it works. Demoivre's theorem says that if we take this complex number, r cosine of theta plus I sine of theta, and we raise it to a power, to the nth power. Now, generally n is an integer, but it doesn't matter. N could be 1/2, it could be 1/3. So we could be taking the cube root of this number or the square root of this number. If it was 1/2, that's what we would be doing. Okay, so r cosine of theta plus I sine of theta is equal to r to the n power times the cosine of n times theta plus I times the sine of n times theta. So we're going to raise the absolute value of the number, a radius value, to the power, and we're going to multiply times the angle. Okay? That means n could be 50. We could be raising a number to the 50th power, a complex number to the 50th power, no less. All right, so that's raising something to a high power like that. How would we normally have to do that? We'd have to take a number like, for example, y'all have this written down? So we'd have to take a number like 2 plus 2i to the 10th power. 2 plus 2i, that's kind of an ugly plus sign, isn't it? Everything about that's ugly. Let's redo it. You don't have to redo it if yours was pretty, but I'm going to redo mine. 2 plus 2i to the 10th power. That's not much better. How would we normally do this? How would you expand this? Remember back to college algebra how we expanded things to high powers? We used Pascal's triangle to find the multipliers for our binomial expansion. And so it would be something like, don't write this because this is not the way we're doing it, but it would start out as 2 to the 10th power times 2i to the 0 power plus some multiplier from Pascal's triangle, 2 to the 9th power times 2i to the 1st power plus some other multiplier times 2 to the 8th power, 2i to the 2nd power. Do y'all remember this process? And then each 9 and 1, 8 and 2, 10 and 0. The next one be some multiplier times 2 to the 7th power, 2i to the 3rd power, etc. Right? That's how we would have to do this using binomial expansion. It would take forever. Okay, it takes forever just to find the 10th or 11th row of Pascal's triangle and do it that way. Okay, so this process is laborious. Our calculators will do this process for us. Everybody get out your calculators. Let me show you a trick. If you have a graphing calculator, and this is why a graphing calculator will not be allowed on the next test. I don't know where your calculator is. Is it up here?
Yeah, it was.
Yeah, come get it then. All right, everybody press the mode key, M-O-D-E.
Oh.
Press your mode key on your calculator. All right. Just type this number in the way you see it. in parentheses. The I key is right above the decimal. You press second and then the period or decimal, and that's where you get I from.
Why'd you just go to mode?
Oh, I'm sorry. Change the mode to A plus BI mode. That's complex mode. My bad.
We were like, where is this type this?
Yeah, I skipped something here. Yeah. So if you change your calculator to complex mode, A plus BI mode, then you go back to the home screen and type in 2 plus 2i to the 10th. It tells you that the answer is 32,768i. Right? Okay. Yeah, hey, that's really easy, right? Now, in the 1700s, they had not the option of punching this into their calculator, changing their graphing calculator to the mode key. Guys, the 1700s, this predates electricity. Okay? They didn't have any way of calculating things. So the people that came up with this were really looking for a shortcut to this expansion method. They would have had Pascal's triangle, or they would have had binomial expansion. I think binomial expansion had already been around because Pascal was from the 15 or 1600s maybe. So the 1700s, they would have had that method for expansion. But Demoivre was looking for and found and proved a shortcut. So the first thing we would do here to use Demoivre's theorem to do this expansion is write the polar form of this number. So this is kind of going through all the skills that we've looked at in this unit. The polar form of this number. 2, 2 is right here, first quadrant. Two is in the first quadrant. What's the angle of that? 45 degrees, pi over 4, right? So our angle, theta, is pi over 4. The magnitude of this thing, if this is 2 and that's 2, what's the hypotenuse? 2 square roots of 2, that's 45, 45, 90 triangle. The hypotenuse is the square root of 2 times the length of the legs. So my radius value is 2 square roots of 2. My angle is pi over 4. All right? So in polar form, this would be 2 square roots of 2 times cosine of pi over 4 plus I times the sine of pi over 4. And we're raising all of that to the 10th power. Right? So this is a culmination of skills. What did we just do? Found the absolute value of the complex number. We wrote it in polar form. That's what we did on the last quiz. You guys all did fairly well on that quiz, so you know this skill. And now I'm going to apply Demoivre's theorem to it. What Demoivre discovered is that this is 2 square roots of 2 to the 10th power. And what do we do with the angles? From Demoivre's theorem, what does the power do to the angles? Multiplies them, right? What's 10 times pi over 4? 10 pi over 4 is 5 pi over 2. Okay? Five pi over 2. 5 pi over 2 is going to be, all the way around is 4 pi over 2. Plus another one. So 5 pi over 2 is right there. Reference angle is pi over 2. And it's on the positive side of the axis, and that's important, right? So the cosine of 5 pi over 2 is 0. And the sine of 5 pi over 2 is 1. So all they would have had to do at this point is 2 square roots of 2 raised to the 10th power. That's not difficult to do. 2 to the 10th power is 1,024. And then the square root of 2 raised to the 10th power is going to be 2 to the 5th. And I can take the 0 out. 0 plus I is just I. (1,024) times 32 is what we just found on our calculators. What was it? 37,268 or 36,728? 32,768. But that's what you actually get if you multiply 1,024 by 2 to the 5th. It's a real time-saving device. Okay? And it's really odd how it works. I don't remember the proof of this from graduate school. We did this in graduate school, but I don't remember the proof of this theorem, how it always works. But this is an interesting concept. It's a great way to expand the binomial. I wonder if there's an application to this, to expanding our... It'd be nice if you could do x plus 3 to the 17th power or something like that using this method. But it wouldn't work because they don't collapse. Never mind. All right. You ready? Any questions here before we move to the next example? All right. Next example. Let's have a look at -1 plus the square root of 3i raised to the 6th power. What's the first step? To use Demoivre's theorem, we have to do what? Write the number in polar form. So the first step is to write this in polar form. This is in the second quadrant, right? Second quadrant, left 1 and up the square root of 3. So this is the right triangle we're working with here. Left 1, up the square root of 3. If you don't recognize what that angle is, you could always use your calculator and do the inverse tangent of the square root of 3 over 1, right? And put it into the second quadrant. But that angle is what? 60 degrees, which is pi over 3. And your unit circle will tell you that that angle is 2 pi over 3. The radius to complete the 30, 60, 90 triangle have 1 square root of 3, and the hypotenuse is 2. So our angle, theta, is 2 pi over 3. And we're raising this to the 6th power. My magnitude is 2. Cosine, 2 pi over 3. Plus I, sine of 2 pi over 3. And we're raising that to the 6th power. All right, what is the cosine of 2 pi over 3? Hold on, I need to do this. 2 to the 6th times the cosine of 2 pi over 3 is what? -1/2. That's correct. And the sine of 2 pi over 3 is square root of 3 over 2. What is 2 to the 6th? 64, isn't it? Yes. 64 times -1/2 is -32. And that's going to be plus 32i times the square root of 3. Because the 2 will cancel with the 64 and leave us with 32. Again, the answer for a complex number has to always be written in standard form for a complex number. Good enough? This is not too bad, right? Y'all okay with this? So the foundational skill that we're working with here is being able to convert a complex number into polar form and then use Demoivre's theorem to come up with it. All right? Any questions before we move? Just going to do this 2 more examples. Let's do I'm making these up on the fly, so hopefully they won't turn into monstrous things. We did a first quadrant angle. We did a first quadrant number. We did a second quadrant number. Let's do third or fourth. Let's do fourth quadrant. Let's do 1 minus I to the 7th power. No, make that 6th power. 7 would have worked. It's okay. All right, let's switch it back to 7. Make it a little more challenging. Okay, first step of the process of doing this using Demoivre's theorem is to write the number in polar form. So I need to find the angle and I need to find the magnitude. So 1 and -1 is there. That's 1, that's -1. What kind of triangle is this if the legs are the same? 45, 45, 90, right? So my angle there is pi over 4 in the fourth quadrant. Now, you could go all the way around to that angle in a positive direction. It would be what? 7 pi over 4, but then we would have to multiply that by 7, which would give us 49 pi over 4. That's a lot of pi's over 4 to count out, right, if we're graphing it. So what might be the smart thing to do for our angle there? Use negative pi over 4 instead of using 7 pi over 4. What's the magnitude of this number, the absolute value of this number? 45, 45, 90. What's the length of the hypotenuse? Square root of 2. So the magnitude is the square root of 2. That's my R value. The angle that I'm going to use is negative pi over 4. So this is going to equal to square root of 2 times cosine of pi over 4 plus I sine of pi over 4, negative pi over 4. That's a big deal right there. All raised to the 6th power. You know, I don't know why I keep bouncing back and forth between 6 and 7. But yes, we decided to do 7th. It's going to complicate things a little bit. Not much. Okay. Now we can apply Demoivre's theorem that we have the number written in polar form. We can apply Demoivre's theorem. So that would be square root of 2 raised to the 7th power. All right. Cosine of negative pi over 4 is going to become cosine of negative 7 pi over 4 plus I sine of negative 7 pi over 4. Now, we need to convert it back to standard form. Where is negative 7 pi over 4? It's in a negative direction, right? If I went all the way around, that's negative 8 pi over 4, right? So negative 7 pi over 4 is in the first quadrant. And that's where I'm getting blank stares from people. Because I have to evaluate the cosine of negative 7 pi over 4. I know my reference angle is pi over 4. I just need to know which quadrant to put it in. So this will be the square root of 2 raised to the 7th power. Let's just leave that as square root of 2 raised to the 7th power for now. Cosine of negative 7 pi over 4 is the square root of 2 over 2. And the sine of 7 pi over 4 is also the square root of 2 over 2. Okay? Now when you distribute this thing, what do you get? What's the square root of 2 to the 7th power times the square root of 2 to the 1st power? Isn't that the square root of 2 to the 8th power? Which is 2 to the 4th power over 2? Which is 8? Eight plus 8i. Now, there were some difficult computations in that one. I'm not likely to give you one that's going to have, I will kind of want to stay home and do some things. This problem would have been much easier if it was to the 6th power. That's why I almost changed it. So we would have had 3 pi over 2, negative 3 pi over 2, that's pi over 2. We would have had some zeros and ones to deal with. But in this case, we had to improvise. And the square root of 2 raised to the 6th power is just 2 to the 3rd, which is 8. So it would have been easier to deal with at the beginning of the problem. All right? Now, let me show you one other application of this. So far, all we've done is work with positive exponents and integer exponents. What if we wanted to do something like the square root of 8i? Not square root. I don't want the square root. I want the cube root. Cube root of 8i. (2i), that's your best guess? See, negative 2i, we're guessing at this, but negative 2i times negative 2i times negative 2i might work, actually. But that would give us negative 8i cubed, and I cubed is negative I, so that would be 8i. Now here's the tricky part of this. In complex analysis, the cube root of an imaginary number, there's 3 cube roots of every imaginary number. Okay, so when we apply Demoivre's theorem, what we're going to get is one of those cube roots. We're going to get the principal cube root. So, I don't know if negative 2i is the principal cube root or if it's just one of the other ones. We'll see. How would we apply Demoivre's theorem to this? It's equal to 8i to the what power? Cube root is the same as the 1/3 power, right? And now I need to write 8i in polar form. 8i, that's right up here. 8 units from the origin, right? So my R value is 8, and my angle is what? Pi over 2. 90 degrees. Okay? So this is going to be 8 times cosine of pi over 2 plus I sine of pi over 2, all raised to the 1/3 power. Now we can apply Demoivre's theorem. This will be the cube root of 8 times the cosine of pi over 6, is 1/3 times 1/2 is 1/6, right? Plus I sine of pi over 6. Met some friends of yours over the weekend. Yeah. Can't remember their names.
Where?
They went to school here but moved to Christian Brothers. One of them moved to Christian Brothers.
Cooper?
Cooper. Yeah, it was Cooper. Yeah. Yeah. We're at the same crawfish boil. Small world. So what's the cube root of 8? 2. And the cosine of pi over 6 is the square root of 3 over 2 plus I times the sine of pi over 6, which is 1/2. So this would be equal to the square root of 3 plus I. So negative 2I is not the principal square root of 8I. It's one of the square roots, but it's not the principal square root. The principal square root is the square root of 3 plus I. I didn't know where that was going with that, but that you were correct to find one of them. There's 3 cube roots of 8, and you can use Demoivre's theorem to find them all, but we're not going to go past just the principal square root. This is the principal square root of 8I. Cube root, excuse me, the principal cube root of 8I. Do y'all think you can handle that? One other thing that we need to look at is if we were raising something, because it also works with, let's just say we're raising, let's start with a number that's already in polar form. Let's start with 2 times the cosine of, let's do pi over 6, plus I times the sine of pi over 6. This is kind of the number we just looked at. Let's raise it to the, let's raise this to the negative 3 power. It still works the same way. We have to raise 2 to the negative 3 power. What's 2 to the negative 3 power? 1/8. Cosine of 3 times pi over 6 is negative pi over 2. I sine of negative pi over 2. Okay, the cosine of negative pi over 2 is 0. The sine of negative pi over 2 is negative 1. So this is equal to 0 minus 1/8 I. So it works for integer powers, positive or negative integers, and also works for rational, taking rational powers, roots of complex numbers. We could take the 2/3 power, the cube root of it squared. No matter what it is, it works. All right, so that's Demoivre's theorem.